And he identified two problems, and I've basically copied these. And you have these notes, so instead of reading them out, I'll just identify the two problems. And one is a lack of sensitivity to adverse pressure gradients. So this was exactly the same problem that a lot of models had, like just standard Sharma, Launder, capsule model. And that's why they wanted to bring a stress transport equation, which we'll look at one more time. So you have a K equation, and you might have an epsilon omega equation depending on where you are in the flow, if you're in the boundary layer or outside the boundary layer, but you're also going to track a single scalar equation for Reynolds stress. And they picked the principal Reynolds stress, which is tau ij, or 1, 2, excuse me. So that was one major issue. The second major issue is, for a lot of reasons outlined here, is the standard capsule models are viewed as numerically stiff, meaning they're hard to evaluate with a computer, and the model formulation would have to be done in a way so that they have robustness of the model and can converge the solutions and not have those types of problems. So there's a few notes and takeaways of this. One is the major model idea, and it's called the baseline model, BSL, of Menter. Baseline, BSL, is to retain the robustness and accuracy of the K omega model, which they use the Wilcox formulation near the wall, and the capsule model in the free stream. And you'll notice these authors have some favoritism, if you will, about their particular models. And so what does that mean? A K epsilon model is going to be transformed into a K omega model, and we'll show those equations in a second. And what does that result in? There's a new term in the K omega model called cross diffusion. Term, and I'll point that out when we look at the equations in a second. And basically, we take the original model and multiply by function f1, and the transform model by 1 minus f1. And the reason we want to do that is we want to blend it. So if you see we take two equations and basically add them together, you can vary some scalar f1 from 0 to 1, and they're blended. So that's called blending, or zonal models, that you have different turbulence models running in different parts of the flow based on some flags or factors. And the question becomes, how do you vary f1? And of course, there's infinite choices, and some are better than the other. And the blending will take place in the wake region of the boundary layer in the original formulation. So, okay, so let's look at some of the major model equations. Here's the original K omega model. And we're going to want to blend this with f1. And then there's a transformed K model, and we will blend this with 1 minus f1. And it's really that straightforward. But you'll see in this transform model, there's, if you just compare them, let's say, omega. So K looks exactly the same, except now there's like different coefficients, and they're just 1 and 2 respectively. So the original has 1, and subscript 2 represents the modified model. And, excuse me, omega. And what you're going to see here is if you compare the omega term, right, the specific dissipation term, 659 and 661, you'll see only one major difference, which I noted above, this term here, which is the cross diffusion term. And that's added in to have blending between K and omega. And let's look a bit at what that means. Also, there's these production terms here for K and omega. They're pretty much remaining the same. So if we look at equations 658 and 659, they're multiplied by F1, as I said. And these two are multiplied by 1 minus F1. And then we would add them together. So we're going to add 659, 662, and 660 and 659 and 661 together. And then we'll get 664 and 665. So this is the blended model, and you can see right in here, here's like this blending terms. So this is a way to blend the two models. And now you say, okay, I've already developed closure coefficients for both models independently. And I don't really want to recalibrate and find them again. So I would take the same blending function and multiply that against my closure coefficients and auxiliary relations. So that's what's noted here. Whoops, wanted to highlight, but that's okay. That's what's noted here. And that type of blending function should look something like F1 times Phi1. So Phi1 would be the coefficients from the first model, and the second one would be 1 minus F1 times Phi2. So 1 and 2 are the coefficients from both models, respectively. And you're going to tie all this into an eddy viscosity model, which connects to the momentum equation. And that would just go as K over omega. There's no factor. Sometimes you'll see people put a new coefficient in here, often called beta. It is not there. And so you have all that, but you want to introduce some additional relations. So you see the model, when you run a modern CFD code, it's called the shear stress transport model. So we could probably look for closure of all this, but we're going to track Reynolds stress. And here's the turbulent Reynolds stress. And this is how Menter's defining it, and eddy viscosity there. And he's only going to track the principal Reynolds stress. And that would be 1, 2. And therefore, we have this simple transport equation. So this is your transport equation. So that's a lot like the simpler models like Johnson-King, which correctly predicts adverse pressure gradient and separation with shocks. Baldwin-Lomax, Boussinesq model, which we previously discussed also as a one-equation model, tracking turbulent Reynolds number with viscosity. Well, here we are. We're tracking K and omega now, which is blended, and we're also tracking this term. So this is why it's called shear stress transport model, right? That's where the SST comes from. So we see the words Menter SST in your ANSYS or STAR codes, and you click that button, you're essentially running this set of equations with this transport model. And this was noted by Menter and others that it's inspired, which I already said verbally, by the Johnson-King model. Right. And it's going to show better predictions than the famous algebraic model of Cebeci-Smith for adverse pressure gradient flows. And you might need to make a few more approximations. You might say that the shear stress, according to Bradshaw's constant, is proportional to K in the boundary layer. And that's where equation 6.70 comes in. On the other hand, typically in these two equation models, you'll have shear stress computed this way with some eddy viscosity times omega, and in a boundary layer formulation that goes partial u, partial y. And then from that formulation, you might write an equation that looks like this. It might go as rho times something like the production over the dissipation times that same constant times turbulent kinetic energy. So that works really well, but in adverse pressure gradients where you especially have shocks, like on a transonic airfoil, this term can become way too large. And so there was a limiter put on it. And that, I'm going to skip this equation for now. Well, actually, no, excuse me, I'm going to keep that in. Using this, we'll say A1K over omega. And there's basically a limiter because this eddy viscosity becomes way too large. And the model without it would lead to infinite in calculations eddy viscosities. And so here's a limiter. And this is nothing but really what amounts to like a empirical correction, where we're setting up a max value for eddy viscosity. So we're limiting eddy viscosity. And that's an empirical correction. So that might go, just as you can see, this should go as K over omega in equation 6.67, or A1K over, let's see, omega, as in 6.73. So you actually have a little switching depending on if you're like in a region of the flow with a huge adverse pressure gradient and shock. And so this is really done for stability, and it's like a correction. Okay. But you still need to add in your blending functions. So I'll just write still need blending functions. And to blend this model, and that was introduced by a new function F2. And these need to be formulated and calibrated still. And so 674 becomes 675, and you'll see they Menter put in this new function F2 right there. Okay, and F2 is very similar to F1. It needs to vary from, say, 0 to 1, but maybe not equal to. And it needs to extend way farther out in the domain. And this is, let's do that. This is Menter's proposed form for F2, where here's an argument of it. And so this is just form to blend F2. And in his paper, I left out figure 3 here, sorry about that, but that's in Menter's original paper. I think I put that in Canvas. If I haven't, I'll still do that.
What does that 222 mean?
Oh, I think this is a typo. So this is just argument sub 2. Sorry, because that's right there. I know, oh, it's squared. It is squared. Sorry about that. Bad typesetting on my part. Okay, so this is where the formulation stands right now. And we still need calibration, of course. And, we'll also, for calibration, we need to look for F1 to fall to 0 within the boundary layer, right? And also for F2. So this was done and calibrated with these particular set of coefficients here. So these are Menter's calibration coefficients. And it's done with what he views as a pressure blending function. So a few summaries and notes. Because you need to form these functions, they call it a blending model or zonal model that activates in different parts of the flow. And the good thing is you don't need to know anything about the flow field in advance, which is really good. And the problem is, where am I here? Yep. So we want to just look briefly at the formulation. So this is, there's no problem, excuse me. This is the formulation with Wilcox's summary. So if you open Wilcox's book, this is the way he presents the final equations. And what I like about that is he puts them all in a form where it's on one page that it's easy to reference and also program. So you see, here's this final blended function f1, and you can see it varies as hyperbolic tangent. So that's a function that should be fairly smooth, right? So it varies from, I think, -1 to 1 when it's in odd function about the y-axis. So we have 1 PdE for turbulent kinetic energy, 1 for dissipation. You have your cross diffusion term here, and you have this blending function f1. So here's these two equations in addition to your Rand's equation and energy equation if you want to do compressible flow with a gas law. F1 fits in here, so this is the blending. And these are these terms which were calibrated against wall flow with that limiter for an eddy viscosity that's bounded. And these are the other terms in the model. This is the form from F2. It's inspired also, so you also have a hyperbolic tangent, so that varies smoothly from when you put this in, 0 to 1. And there's some limiters that are added to limit production. So this was done partly with calibration, and then here's all the coefficients noted. Now, that's the base model when you run Menter SST. And then people said, well, we might want to try and save grid resolution near the wall. And for these models, one nice thing about K omega is that the wall-bounded flows well behaved, which is a good thing. And often you could get away with y plus calculations in the range of, say, less than 1 to, I don't know, maybe 50 to 100, with small error, about 2% error. And this is one particular figure from the Wilcox books in 6.4 of a simple flow. And in this flow, they had about a y plus 0.2, 9, and 100. And they calculated, so that's grid point spacing, right, near the wall. And then here's the figure. So 3 velocity profiles. So you see a typical log layer, right? So this is wall distance, y plus, just like your projects. This is the velocity normalized in inner coordinates. This is the log region. I've seen this many times this semester, but it's good to emphasize that the viscous region. So they call it low Reynolds number mode simply because they have grid points near the wall. And they also used wall function for other cases. So for the y plus 100 case, they imposed the known composite profile solution and matched it. And then here's a case where y plus is about 10. And they all have similar results, but nothing beats the model and resolution near the wall, because you don't have to use a wall function at all. And I wouldn't recommend using wall functions when your flow isn't in equilibrium, e.g. near shock waves or something like this attached to the wall. So now we have this complicated blended K epsilon, K omega model with limiters and a shear stress transport term, and it's very predictive against, say, transonic airfoils and a wide range of flows, wakes, shear layers, boundary layers, jets, and using one set of coefficients, but it's not a universal model. And people said, well, what happens when flows are separating or they have large unsteady regions? And this is when they said, well, why don't we combine LES with RANS? So RANS is what we've been mostly talking about this semester. And then there's another approach, as you know, called large eddy simulation, where we're trying to only simulate the unsteady energy-containing eddies. That's why they call them the large eddies, because the largest eddies of the flow contain most of the turbulence. And so the question becomes, how can I combine the advantages of both approaches, the speed and accuracy of, say, RANS models for boundary layers and shear layers, with, say, capturing the unsteady wakes or large unsteady separations of the turbulence? And so that's the question. So you would only, and you want to do this automatically. You know, you don't want to go into your CFD domain and say, okay, I'm going to paint, you know, this part of the domain is like LES, and I'm going to paint another part of the domain, which would be done with RANS. I mean, you could do that, but then you have to blend the RANS and LES regions, and it takes a lot of user input. And then people would say, oh, well, that's not even a closed turbulence model because you're telling us in advance something about the solution. And so people thought, okay, I want to try and create a method to do that automatically. And that's what has come into being, and people call sometimes, I'm going to skip some of these graphs, the zonal formation. So this is like RANS plus LES. And there was definitely different people formulating these things for a long time, but I believe in our community that a lot of the credit went back to, once again, Philippe Spalart. His name comes up a lot. And that's called DES, detached eddy simulation. So some people call it DES. Some people might call it Zono Methods or zonal formulations. And another part of the community might call it hybrid RANS, LES. And I think these are some of the subjects that the seminar speaker will be touching on next week for wind turbines. As you can imagine, in a huge part of the flow field, you basically have a stationary field, which you can simulate with RANS. And when you have, like, say, wakes off of wind turbine blades, you can have an LES formulation. And you want to blend these two approaches and models seamlessly. So the original contribution of DES into either a capsule or Spalart one equation model, or the Menter SST model, for example, DES, detached eddy simulation for Menter SST, can be done very simply. It's just a matter of reformulating the capsule part of the capsule model and adding a new factor called FDES, which is just a function for DES. And here's the function here, which is a max of a length scale. So what is LT? That's like a turbulent length scale. Delta is the grid point spacing. And I believe that CDUS is a coefficient. So here, here's one definition of your length scale. You see, so LT is nothing but the square root of K divided by omega times a coefficient. And I think usually beta star is a 0.09 in the typical closure, if I remember. And CDS is another calibration coefficient. And delta is the local grid point spacing, and say, if you have a structured grid, that'd be the max of delta X, delta Y, or delta Z. So you can see in your code, you can actually implement this quite easily, but then you have to have a whole nother sort of code, an LES code built in, which would transition your solver. That's really how easy it is. And one explanation is like, I'll zoom in here to write it. Say, if the grid spacing, wow, feel back like I'm in kindergarten again, huge crayons on paper. If the grid spacing is smaller than L, the length scale, then perform LES locally. And it doesn't turn out to be locally in practice, it actually turns out to be large regions. And if you implemented this model, if you took your well-validated Menter SST model with limiters, and it's validated across many flows, and there's no flow separation whatsoever, and I implemented the DES model and turned it into DES code, I would rerun it. And it should give me exactly the same prediction as it did before if there's no separation, because it should kind of be a RANS model everywhere, ideally. And then if I took the same code and say put my airfoil, for example, at high angle of attack, I would get separation, then I shouldn't have the same result as the original steady RANS code, or even unsteady RANS. So here's an example of that. This is the original model, and so here's a airfoil, and you do have some separation right there on the suction side near the trailing edge. And here's a few different implementations by different authors. This is CFX, that's a particular software. So these two cases are exactly the same except for the grid point distribution. So you see the cases are actually sensitive to grid point distribution. Why? Because it depends, you're switching from your RANS model to your DES or detached steady simulation model depends on your minimum grid point spacing. So sometimes these models, especially early ones, are even more sensitive to grid point spacing. So without getting into too much detail, I want to say that a lot of the work in this DES field has been to try and create models which are less sensitive to grid point spacing. And I'm really familiar with detached steady simulation codes because that's what I did my master's degree on. I did my master's thesis on writing my own detached steady simulation solver for wind turbines. So I remember I was in Penn State and my advisor took me out to a wind turbine field and we looked at him and said, wow, that's big and complicated looking. And he said, oh yeah, Steve, I have funding from the National Renewable Energy Lab and we're going to be running HP simulations using detached steady simulation with Menter's SST model combined with LES. And we have 2 years to do it. So I said, oh, I better do some work, I guess. Yeah, okay. So watching these simulations here brought up a lot of painful memories of months of debugging and not tears, but, you know, long hours in the lab. Anyway, I'll let you read through some of this yourself. But what I want to do is just look at a few cases here of what you might see in a typical DES result. And here's one case in figure 6.8. So this is a channel flow. The flow moves from left to right in this figure. Let's just zoom in there. And you can see there's just basically like a cubic or rectangular type body attached to the wall of the wind tunnel. So people have done experiments like this in the basic aerodynamics wind tunnel, the BART of NASA Langley. Very well controlled, high quality turbulence measurements. And they use those measurements to benchmark their new turbulence model developments. So there's the flow left to right, center of the channel. This is a side view, so it goes half the height of the channel. And this is what one snapshot of time, so this is at one time. And there's absolutely no specification in the flow field by the user whatsoever of what regions of the flow are basically become like a steady round simulation, what becomes separated. So anyway, these are isosurfaces of this quantity. And you can go in here and you can see there's this strange like bow vortex, I would call it. And these little points here are the streamlines on the surface. And this black thing is that cube right here. So you can kind of see it in there. Because I should have done with red or some other color. And then these are all the shedded vortices. So for those of doing LES, you could easily run an LES on this simulation and probably get similar results. But you won't have resolved the boundary layer as well as a DES code, because you don't have all the advantages of, say, K omega models. On the other hand, the people in the LES community are creating their own wall-based LES models to resolve the boundary layer with only a LES code. So now there's like two worlds of thought. I'm only going to do LES but use wall models because I can't afford to resolve the boundary layer, or I can do a DES and resolve the boundary layer and have the advantages of the LES. Which one's cheaper computationally?
Just the LES.
Well, it actually turns out the DES is cheaper. Yeah, because you're only solving an LES in this small part of the domain, which is the wake. The rest of this flow field is all basically reduces to a steady rounds calculation. So if you look over here, and this is what I would never do as like a CFD user, but I can actually paint it in. I would say this region's the wake, right, in purple. Green and purple, those are not complementary colors. The graphics design students will yell at me. And so everywhere else in the domain, which is rather large, is going to be a steady rounds type solution, which is always cheaper than LES. So anyway, it's an interesting approach, but today I see more people doing LES than DES. And I would say, well, why is that? Well, one is it's way less complicated. And a lot of people might say, oh, you know, we've done everything we can today with RANS. But that's where you might say that's where comes in new RANS research, which might be in these traditional models or Reynolds stress models. Oh, and here's a good graph of the experimental data. So experiments are points, flow is left to right. There's your cube right here. So this is their flow direction. And let's see here. Then there's two predictions. One is your standard Menter SST model, which we just looked at the blending of with limiters and everything. And then this is the Menter SST model combined with the detached eddy simulation formulation, which is just a switch to an LES code regionally. So here's the wake region, this region here. So this is all going to be DES. So I did two simulations in comparative experiment, one of pure SST and one of pure with the DES approach. So let's look carefully. It looks like the RANs are these dash dot lines, and the solid lines are SST DES. And we would expect the results from both approaches to be exactly the same outside the cube in the free field, right? So this is the free stream region right here. And sure enough, I don't see any differences between the predictions of RANS and DES. So that's a good sign that I did not only have it programmed correctly, my code, but the results make physical sense. If that wasn't the case, I would kind of pause there. And then you look in the wake, and I would hopefully the wake's different, or I've done this huge expensive computation for nothing, right? And you can see the LES, or excuse me, the RANS results are, say, here in the wake at 6. Well, this is a 2 cube lengths downstream here. And then the experiment and the DS are much well aligned. In fact, the further I go downstream, I actually have better results, which is curious in itself. Okay, so that's just a quick example, well, actually two examples of an airfoil with very weak attachment near the trailing edge, which shows the sensitivity requirements for DES, and a bluff body type flow, a wake flow, simple incompressible low speed flow in a wind tunnel to kind of benchmark these solvers. So with that, just make sure I don't have any other major notes I want to say about these methods. No, I don't. So I think the next topic we'll talk about is how do we overcome some of these limitations with the traditional approaches and attack the very difficult problem of Reynolds stress transport model closure. So we'll talk about after a small break.